Have you ever thought about what it would be like to send electricity around the entire planet with absolutely zero loss of power? I know, it sounds like something straight out of science fiction, right? But it's a real phenomenon, and it's called superconductivity. So today, we're going to dive into this incredible science of perfect efficiency and explore how it could literally change everything.
Just take a second and really picture that. A wire where electricity just flows perfectly. It's a pretty simple idea, but oh man, the consequences are massive. A world without electrical resistance? That means our devices would run cool, our power grid would be 100% efficient, and technologies that we can only dream of today could suddenly become a reality.
You know, it's kind of like a garden hose with zero leaks. Every single drop of water you put in one end comes right out the other. Well, that's superconductivity for electricity. None of the energy is lost as heat, which means we could power our entire world with an efficiency we've never seen before. I mean, this is a total, fundamental shift in how we even think about energy.
Okay, so there's a name for this crazy phenomenon, of course, superconductivity. Now the key here, the really important part, is that it only happens below a critical temperature. This isn't just some everyday property of materials. It's a whole unique state of matter that only shows up under very specific and very, very cold conditions.
And, you know, this isn't some brand new thing. We've known about this for over a century. Way back in 1911, a Dutch physicist named Heike Kamerlingh-Onnes was pushing the absolute limits of cold, messing around with mercury at temperatures just a few degrees above absolute zero. Now, he expected the resistance to go down, sure, but what he saw, well, it was something that shouldn't have been possible. The resistance didn't just drop, it vanished. Poof, gone.
All right, so how does this actually work? What's the secret to unlocking this amazing zero-resistance state? Well, it all comes down to temperature. Think of it like every superconductor has its own special on-off switch for its incredible powers, and that switch is its critical temperature. You can think of it like water turning into ice. Right at a specific temperature, its properties completely change. It's the same idea for a superconductor. This freezing point for resistance is called its critical temperature, or we just call it TC for short. Once you cross that threshold, the material just transforms into a perfect conductor. So above its critical temperature, a material acts, well, totally normal. Electrons are kind of bumping and crashing their way through the atoms, creating resistance and wasting energy as heat. But the moment you dip below that TC, something incredible happens. The electrons pair up, and they just glide right through. No friction, no resistance, nothing.
But wait, there's more. Zero resistance is just one of the superpowers these materials have. The other one is even more mind-blowing, at least visually. It's the ability to levitate. And this leads to something that looks like straight-up magic, but I promise you, it's pure science. It's all thanks to something called the Meissner effect.
It's called the Meissner effect, and it's a huge deal. See, it's not just that superconductors don't care about magnetic fields, they actively kick them out. When a material becomes a superconductor, it pushes any magnetic fields out from inside itself. This is the property that really separates a superconductor from just a hypothetical, perfect conductor. Think of it like an invisible force field. The superconductor creates these tiny little currents on its surface, and those currents generate their own magnetic field. And that field perfectly pushes back against the one from the outside, creating the zone inside the material where magnetism just can't exist.
There's actually a word for this perfect repulsion of magnetic fields. It's called diamagnetism. Now, pretty much all materials have a tiny bit of this property, but superconductors, they take it to a whole other level. They are perfectly diamagnetic, which is exactly why they can float so effortlessly above magnets. Okay, so let's put it all together. You take a superconductor, you cool it down below its critical temperature, and you have a magnet nearby. The Meissner effect kicks into high gear. The superconductor shoves the magnet's field away from it, creating this incredibly powerful repulsive force that can literally overcome gravity. It's quantum physics happening right in front of your eyes. Now, zero resistance and magnetic levitation aren't just cool party tricks. They're the actual foundation for some of our most advanced technologies. Superconductivity is already out there, working all around us, in everything from hospitals to high-speed trains.
You know those MRI machines in hospitals? Yep, those incredibly powerful magnets inside, they're superconducting. That's how they create those amazingly detailed images of our bodies. And what about high-speed maglev trains? They use superconducting magnets to float above the tracks, which gets rid of friction and lets them hit incredible speeds.
They're also at the heart of giant particle accelerators, like the Large Hadron Collider, and they are absolutely essential for the quantum computers that are going to power our future.
But here's the catch. There's always a catch, right? All of this requires extreme, extreme cold. And that's the biggest barrier we have to unlocking the full potential of superconductivity. But what if we could break that barrier? What if we could create a material that superconducts at room temperature? It wouldn't just be an improvement, it would be a complete game changer. Our computers would be thousands of times faster. Our energy grid would be perfectly efficient. It's the holy grail of material science, and finding it could truly redefine the future of civilization.